So this session will be a question and answer session. I'll go through some questions that I've received over mail and Twitter and just try to answer them one by one. I haven't really prepared any answers, so I'll just answer each question sort of in the moment. And if you who are on the call have any additional questions that aren't covered here or think of something, just type it in the chat or speak up. So first we have two questions here from Rick Appleton. First question is regarding the plugin interception points. Is that not handled by your high-level game loop in Lua? Is granularity too big? So this refers to the problem that I talked about when you create a plugin system, that you typically want to have callbacks out to the plugin at different points so that the plugin has a chance to do something when, for example, a level is loaded, a unit is spawned, and so on. But you run into a problem then, because what should the callback points be? It's very easy to think of lots of different situations where you would need a specific callback. But if you start to insert callbacks everywhere, the code becomes kind of messy. So yeah, the question here is, since we're driving the game loop in Lua, can't we just do whatever Lua calls we want to the plugins in between the calls we make from Lua to do stuff? I would say not really, and the reason is that the granularity is too big. So from Lua, if we look at how we update worlds, originally we only had a single update command from Lua that would do all the updates in the world, so animation, physics, and so on. And now we've split that in two parts. So we have update. You can either do a single update, or you can update, I think it's update animations, and then update the rest of the stuff separately. So you can split it in two calls in Lua. You could drive this further and sort of split it into more update calls. You could separate update physics in the world, update animation, update some other thing, and then you could sort of insert these plugin interception points in between these calls. But that sort of puts you in the same problem as with inserting these plugin calls, just from a different direction. Now, instead of trying to figure out where you insert these plugin interception points, now you need to figure out, well, how should I divide these calls in Lua? What kind of calls should I have? So now you have update animation. Oh, maybe you want to split that up into update state machines and update low-level animations and update animation blending, or maybe you need to split it even further. So you end up with the same sort of messy question of how to split things up into smaller parts. You can insert different things in between them, whether you sort of tackle this issue from the Lua side or from the plugin side. And in addition to that issue, like how do we divide things, we still have stuff like unit spawning. Like maybe you want all your plugins to react to when a unit or an entity is spawned, but that doesn't necessarily come from Lua. There are other systems that can trigger spawning of units, like Flow or typically from Flow or Lua. So how do you do that then? Should you handle it in Flow, then add like explicit callbacks to plugin systems in Flow wherever Flow might spawn a unit? So yeah, not super easy question, not super easy to solve this from sort of the Lua side. We still have kind of the same problem. So the next question here from Rick is, well, allocators are C++. Your plugin API is C. I noticed an Allocator API ID to get allocators in the plugin. Can you give details on how that works? So the allocators in the onion, we have a base allocator class that everything allocates from, and then other allocators such as a heap allocator, temp allocator, they inherit from that. So how do we, this is a C++ class, but we have a plugin C API that uses this allocator interface, and what's up with that? Yeah, we've chosen to have a C interface, which is that's the most useful thing, but nothing prevents us from exposing classes like these over the C interface, and that's actually what's done in this Allocator API. So let's see if we look at the plugin API. This is the right one, right? So Allocator API here. So yeah, so what we expose here in the C, oh sorry, it's all the way. What we expose here in the C API is an allocate function that takes an allocator object pointer, which will, that's just a C pointer, it will point to an allocator object and what we want to allocate, and a similar deallocate function. And this function will just cast this to the appropriate C++ object and do the call on the allocator. So this is just sort of the C++ or the C way of implementing objects that we make use of here. And it's similar, I mean, a lot of the things that we expose in the engine are C++ classes, but we expose them through a C API interface in this way by using an abstract struct in C. So C doesn't know what this pointer refers to. From C, it's just a pointer, but it refers to an actual object on the C++ side. Now, this is not the only way to use allocators in the plugin. The plugin could also use some other mechanism for allocating memory, but usually we want it to be a part of the engine's memory. I mean, the plugin could just call malloc and do whatever it likes, but usually it's better for the plugin to go through the Allocator API because we want to track the total use of memory in our system, including the memory used by plugins. So that's why that is the recommended way of doing it. Right, we have some questions from Jeremy Saint-Amand, or just one question. So, concerning entity components, are there any ways to minimize entity lookups in a component when communicating between different components? What happens in a real game scenario is that there are lots of intercommunication between components, and the only easy way to do this is to look at a ton of entities, sometimes each frame. What is the best way to do communication without looking at the instance by entity? So if you remember, in the component system we have something called, we have like a hash map that maps from an entity ID into a component index, and so the components are laid out in a buffer in memory like this. Component data, instance data, and to find the component for a specific that matches a specific entity, we'll look up in this hash map table to find the index here where that component resides. And as Jeremy correctly says here, this can be a problem if we have a loop in one component where we loop through a lot of things and then we want to access another component, so we do a hash map lookup here, and that can be really expensive. Now, this is kind of easy to optimize. We haven't done that yet because we haven't really run into this situation so much, but in this component data, one thing we store is the entity is stored with each component here. It's actually splattered out into a structure of arrays rather than stored in a single array, but I'm just showing it here for reference. So the entity is stored here, so instead of having just a lookup function from entity and get the index of the component, what we could do is that this component here that uses this lookup could cache the last result of the index from each frame, because typically probably we would do this each frame. If we only do it once, it's not really a performance problem. So if we do this each frame, we could cache this index, and then we could do a lookup based on entity and the old index. And if we have this lookup function then doesn't have to go to the hash map immediately. Instead, it could go directly to this buffer table and check the element at this index and see, oh, is this element here? Because what might happen, why we need this lookup table, is that we might move these elements around. As something gets deleted, we delete it and put another thing in its place and so on. But probably that hasn't happened. It's pretty rare that we move things around. Most likely things will be in their same place. So if we have the old index, we can just start by checking, oh, is that thing still at the old index? So just a memory lookup. And if it's there, then we return it immediately. If it's not there, then we go to the hash map and do the proper lookup. So that way we can sort of optimize away the hash table lookup. Now, even with the hash table lookup optimized away, we can still have performance issues, because as we access data in a different component here in the loop, if we have really a lot of items in it, we will get a cache miss because we access some memory stored somewhere else. So if you're writing a component where this is a really common scenario, that you want to iterate over all the instances of some other component, then you might consider caching that component's data inside this component, so to have it sort of hot in the cache. So in this case, maybe say it's the position that you're interested in, then you could, in this component which needs the position, you could just store the position in addition to the data that is specific for this particular component. Now, if you do this, of course, you need some mechanism to update this position when it has changed in the component that owns the position. So you need some notification system for dealing with changes and so on. And this kind of requires that changes are infrequent, so that, I mean, if all the positions of every object changes every frame, then this won't optimize anything. But typically the positions are mostly static, which means that you will have a small list of positions that you need to update, and then you will have everything is in hot cache for this tight loop that you need to perform here. So that's how you can optimize this. Then we have some questions from Per, who's on the call here, so he can correct me if I misunderstood something. So the entity hierarchy and the scene graphs both form a transform hierarchy. Do you ever consider having just a scene graph or just using entities? Yes, I have considered both those things. I'm not super fond of having this big scene graph, because it tends to tie everything together into a single thing, which means that it becomes kind of tricky when you want to reorganize it. And that's kind of the difference here, that this entity hierarchy will typically be reorganized. As new entities are spawned, they will be linked into this hierarchy, and as they're unspawned, they will be removed. So that entity hierarchy is constantly changing, while as the scene graphs are static usually. Usually you have like a bone hierarchy, a way the skeleton is linked in an animated character, and that thing will never change. There are some situations where you might want to change the scene graph, like reroute the character for some specific animation purposes, but that's typically super rare compared to how often the entity hierarchy is changing. So by splitting these two separately, we can kind of take advantage of the fact that this is mostly static, and while this is changing, and sort of do our optimizations for these two cases. Whereas if we had just a big scene graph, that thing would be constantly changing, which would make it harder to reach some performance goals. Yeah, you could just use entities too. The problem there is if you have an animated character with like 120 bones in it, then to just use entities, you would have to, that character would then suddenly be represented by 120 entities. Might not be a problem if like every part of the entity system is really super optimized, and things like this, lookups like this in the previous question, and everything is really super optimized. Maybe having 120 entities is in this character is not a bad thing, and having meshes being driven by, because what would happen here is of course that the skin mesh of this character would be driven, the skin mesh would be somewhere in this entity hierarchy, and it would be driven by all of these other entities, and maybe that wouldn't be a problem, but it's kind of seems, I don't know, it seems like risky in that way that we are creating lots and lots more entities to keep track of, and potentially we run into more performance problems, and potentially it becomes a bit messy to have all these hundreds of entities and display them sort of in the entity graph and so on, when the user might not think of like each part of each individual finger of a character as a separate entity. But there are benefits to it too, like it reduces the amount of concepts that we have to deal with by putting it all in the same place. So I think it could be argued, both these two approaches could be argued, but yeah, for these reasons I went with this approach, the approach we have to have like both scene graphs and the entity hierarchy. Okay, next question. The entities system uses component instance IDs and component instances to support garbage collection. When we need to store a reference, we use the instance ID, and want to interact, we use lookup from ID to instance. Can you talk a little bit about the design decisions about this? So what is meant by the instance in this case for entities, these concepts can be a little confusing, but when we talk about the instance of a component, we just mean its index in this component buffer. So the instance is just some index I here, which we can use to quickly find the component's data. It's just an array lookup, right? Whereas the component instance ID, it's a permanent ID that is associated with each instance here, and that we can do a lookup from. So in the lookup from the table I showed earlier, I looked up just on the entity, but an entity can have multiple components. So to distinguish between a component instance belonging to the same entity, we have IDs. So in this case, we would use the hash map from entity to instance. We would use that to sort of look up the first component that belongs to the entity, and then we would follow next links in the components to walk all the components that belong to the entity and compare their IDs. So the reason for having both these concepts, both the instance and the ID, is that to use the ID, we need to go through this lookup table and through this hash map and look up the instance before we can get to the actual data. Whereas with the instances, we have just a simple array access. So the array access is faster, which is why we want to use that as much as possible. But the array access might not be permanent because we reserve the right to reorder the elements in the array here. So we're not guaranteed that the array is permanent. The array index is permanent. So So in that case, we need something other to permanently define it, which is the ID. So, and then we have this sort of general policy in the engine that we shouldn't incur any, I mean, we could just use the ID and always take the hit of the hash map lookup, but we have this general policy in the engine that we don't want to put unnecessary costs on the user. So we don't want to force the user to always use the ID. So that's why we have both these concepts. Another thing we could do is that we could say, well, in fact, we're gonna say that objects will always keep their position in this array. So we will never move objects around in this array. So once you have this instance ID, it will always point to the correct location of the component, unless the component is deleted. As long as it exists, it will exist as this index. That might not be as immediately obvious, but this has kind of a performance hit too, because if we delete a lot of component instances and we can't move these around, that will sort of leave holes in the component array here. We're forced to leave holes if we delete things and we can't move things around. Now these holes might be filled later, of course, as we create other components, but for a while we might have holes here, which means that later when we want to iterate over all instances and do something, if we have like a real number crunching loop, we will access a lot of memory that we don't really use. So we are sort of wasting cache space and so on. This is might not be a super big problem. It sort of depends on how the system is used. But again, we don't want to put the user in a situation where we sort of force a bad situation. In this case, we're forcing a bad performance on the component writer, because the component writer can't really do a super efficient memory layout. So that's why we've sort of decided this slightly more complex approach, but more efficient approach. But you could decide that, like you could decide in your code that no, I'm only going to deal with IDs, and then you could make your own interface to our systems that sort of never uses the instances. It always does the lookup behind your back from ID to instance, and then you could get this high-level interface. And that's why we like having these lower-level interface, because it gives our users the option to choose. They can choose to use a high-level interface if they want to, by just writing an abstraction layer on top of our interface, but we don't take away the opportunity to have a good performance. So then finally we have a bunch of questions from Laurie Hedge, and I'll go through all of them here. So you mentioned that all your strings are encoded in UTF-8. Do you find this causes any problems, such as not being able to index the string in a meaningful way, and so on? I would say no to this question, because actually indexing the string, so the problem here is, of course, if you want to index the string, not by byte index, but by sort of character index, that can become kind of complicated, because some characters are 2 bytes wide and some are 4 bytes wide and so on, so we don't really exactly know where the character borders are. I don't think this is a problem at all for game engines, because we typically don't do that kind of string manipulation, like get this character of the string, the ETH character of the string. Also, if you're going to do this for real, it's also really hard, because you have like all the complexities of Unicode with like combined characters, like characters that stack on top of each other. So even if you used UTF-16, which is a horrible format, because then it's mostly just 2 bytes per character, but not all of the time, which can really mess you up. But even if you used full code points, like full integers for this, because of these combining marks, you still can't really go strictly from an index into the buffer into an index in the character count, because you have these combining marks that you still want to treat as a single character. So it's kind of a really messy issue, but I don't think it's not a big problem in practice, because we don't have a lot of these indexing operations. Pretty much the only way where we need to do this indexing is where we do the final render of the string. So we do line breaking and converting it into glyphs. Then we have to go into actual character format. But in that case, we do it from start to end of the string. And then there is no particular cost to it, because we can enumerate the size of each UTF-8 code point as we walk along the string. It's only this sort of random access into a character at a specific character offset of the string that we can't do efficiently with this encoding. But as I said, this rarely comes up in practice in game engines. Okay, so one of the reasons for using sharp pointers and array is to avoid dynamic string allocations. However, using UTF-8, do you find that you're constantly having to convert this in other formats not to use them? No. Again, we don't have a lot of these indexing operations, so there's not a lot of situations where we have to do this. I mean, we have to do this when we call out to system functions like system libraries, like in Windows and others. But internally in the engine, we never do this really. The only place is, as I said again, when we do the actual glyph rendering, then we walk to the string and convert and find the glyphs. But there's not a lot of, and that's only one way. That's all of our conversions are only one way. We go from our thing into the other format. And yes, as Oscar says here, we have to do a lot of conversions when dealing with UWP, because again, that's a system library that we need to convert to that format. But one thing to notice too with this question is that in doing these conversions, we typically not do memory allocations, because we only need the converted string for a short while, which means we use our temp allocator system, which will primarily use stack space and only go to heap allocation if we run out of memory. So we can do these conversions without doing any memory allocations. So it's not really a problem in that sense. Yeah, you have to deal with null terminated strings rather than buffer and string length. Do you think that's a problem? Not in a lot of situations, I think. Again, it's not that common that you access the whole string I mean, we don't. All of these questions is really related to doing string operations, and we don't do a lot of string operations in the engine. We don't do a lot of concatenations of strings. I mean, it happens sometimes, but it's not a super common operation. And kind of related to this, I think that if you want to do a lot of string operations, like okay, so we don't do a lot of string manipulation like concatenation and extracting substrings and so on. That's just not a big thing of what happens in a game engine. But even if you want to do that, I would argue that going for std string or something like that, which is, I guess, like the alternative, or your own string class, is not the thing you would want to do, because std string is not super efficient on these kinds of operations either. Like if say that you're concatenating 1,000 strings, using that in std string, just sort of appending each string after another is not very efficient at all, because every time the string grows, you'll have to copy all the memory to a new place. So if you're doing a big concatenation to that, you want some hierarchical representation of the string. For example, you could use like a stack of string with the requirement that represents the full concatenated string, where the requirement that you can only stack a shorter string on top of a longer string. That's like a useful format for doing multiple concatenations on a string, and there are other formats like rope formats and stuff like that. And if you're doing serious string manipulations, I think std string is not your best alternative, because inserting stuff in the middle of a big std string is not efficient either. So in that case, you might consider a different format altogether. With the other containers, one thing that often frustrates me is the tight coupling between data layout and semantics. For example, I often find that I want the semantics of a hash map, but will only have a few elements, so an array of key value pairs would be more efficient. Have you ever considered having containers like boost flat map flat set? Are there any downsides you can see to doing this? So this is kind of funny, because we actually had, or do we still have that container? Let me see. Yeah, we have that container actually. So in our case, it's called sort map, and it's exactly what you're asking for here. It's a sorted array, but you access it as a hash map. So we actually have that in the engine. So there are downsides, I think, here. Actually, I'm not sure I would do that exactly as we've done it right now, sort of hide the implementation behind this interface, because I think there's a benefit to always, I think with containers it's a benefit to know the implementation, to know what's actually going on. So I think designing this, like if I would design this right now, I think I would use standard arrays instead, and then sort of put just an interface above it in order to use it as sort of an in-place dictionary, like an array dictionary. Yeah, but we have that. We have this in our system. So threading. You spoke a lot about design decisions behind decomposing individual systems into tasks, whilst not overlapping tasks with different systems very much. Behind the overlapping tasks from the game thread and render thread. This makes a lot of sense now, but do you see it as being a threat to the scalability of the engine long term? Many modern algorithms seem to be going for a completely task-based approach. Do you think this is something Stingray will eventually have to do? Yeah, I think this is the right way to go. I think this is definitely what you want to do. I think you want a system that's completely free-flowing task, and sort of map out a graph between. But the tricky part here is sort of defining how these jobs flow between these tasks, and who allocates the memory, and when is that memory released, when you need sort of temporary buffers to pass memory between these different tasks, and also how do you lay out the graph of the task so that you get maximum so you can run it in parallel as much as possible without introducing sort of frame delays, which might happen if you try to pipeline things. For example, you could pipeline everything. We could run like animation and physics in the same time if physics worked on the animation data from the last frame, but then we're introducing frame delays, which is not nice, especially in this area of VR where we really want to keep the latency from input to finally rendered image as short as possible. So introducing sort of pipelining stages is problematic. But yeah, I think going more to a task-based approach is definitely the way to do. Even if maybe in the first iteration we won't get that much improved performance out of it, because the graph will just be a serial graph where everything depends on the previous step, like animation, then physics, and so there aren't really any opportunities for parallelization in the graph. But I still think going to a graph formalization is the right move, because it'll allow you to later sort of change that graph around a little bit and find these opportunities for parallelism between the tasks. So I think that's a good way to go going forward. But as I said, there are tricky things to think about, like in which order things run in this graph, and how these temporary memory buffers get allocated and moved and so on. So some questions about testing. Like you, I found unit tests to be really valuable. However, form is I always find I'm running into the problem that game systems by their very nature seem to have a lot of interdependencies. In a normal application, I would resolve this through dependency injection and mocking spoofing. This works well in languages like Java, where everything is virtual, or in dynamic languages, duck typing, like Python. But I tend to find that in games, I don't really want to pay the runtime cost of making everything a virtual interface just to support mocks, when there's only going to be one concrete application in the application that could be statically linked. Do you have any approaches in Stingray to avoiding this problem? I've seen some people discussing link time dependency injection as a possibility. Does your build test system allow for anything like this? All right, so a bunch of things to address here. Well, so I should probably say, for full disclosure, that I'm not really a testing fanatic. I mean, I see the big value of unit tests in a lot of cases, but I'm not super into dependency injection, mocking, spoofing. To me, it seems like once you start going down that path, it's so much effort to write the tests that there is almost no. I mean, I see diminishing benefits once you have to deal with all that stuff. Honestly, to be honest, I haven't done that a lot. It might be my sort of perspective of this would change if I really worked in a code base where dependency injection, mocking, spoofing was like a common thing and something you did all the time. But to me, it seems like just boilerplate right now. That's my perspective of it right now. So I would say that I see this as sort of a design challenge rather on the C side. So I try to design the systems so that they are amenable to unit testing. And I think that if you do like a proper design of the system, then sort of it should depend very little on external things. And the external things it depends on should have like a kind of abstract formulation, either a virtual interface or function pointers with callbacks or something else, so that you can do these kinds of things. And that's stuff like passing in allocators so that you don't have global allocator system, passing in your file system representation so you don't have to necessarily access physical files on disk and so on. So I think we should design the system so that we don't really need to do mocking and spoofing and dependency injection, but that we can work with the natural API of the system, but that natural API is so decoupled that it's amenable but for testing without resorting to duck typing and all that stuff. Let's see. Link time dependency injection. That's kind of cool in its. I wouldn't use it for this, but it's kind of cool anyway. We don't have any support for that right now, but it's something that would be cool to look into. And even things like runtime patching injection of stuff could be done as well, which is kind of cool. Is your integration testing automating system something that only Engine can use, or is it available for testing gameplay code as well? You mentioned the system was underused in the Engine. If it's open to customers, do they tend to use it more? I know some game studios have invested heavily in automated testing. Yeah, it's a Ruby script, so anyone could use it, and it can run arbitrary projects, so it can run game projects too. It's not something we really distribute, like market a lot towards our customers, because yeah, it's not necessarily the nicest system, like hard hacking Ruby code. But it could be used. I don't think our customers use it. I don't know that our customers are doing lots of automated testing. Yeah, I don't actually know what the customer situation is, but as far as I know, they don't use this system, at least. What led to the decision to write test scripts in Ruby? Do you think there is any downside to introducing more languages into the engine? Does Ruby have properties as a language that lend it particularly well to Java testing? Is it possible to use other languages here to drive the test? Yeah, I definitely think there are lots of drawbacks introducing more languages into the engine, and I think we have too many languages in our systems right now, and I think we should try to go on a diet. I mean, the drawback is that, well, now people have to learn another language, and while learning the syntax of a language shouldn't be a big deal for like a software engineer, there's still like there's lots of other stuff that's not just syntax. There's lots of like, oh, what's like the standard way of writing Ruby these days, and what are the sort of libraries you want to use, and then you have the stuff of keeping track with new Ruby releases and updating your gems and references, and so I think there's a cost to introducing more languages, and I would normally shy from doing it. The reason is like, well, we had Ruby quite early in the engine. Originally all our build scripts were written in Ruby 2, and now we switched that to CMake. But Ruby was like one of the first languages of the engine. So the first languages of the engine was C++, Ruby, and Lua were the initial languages of the engine. So C++ for low-level code, Lua for gameplay scripting, and Ruby for system tasks like building the code, downloading libraries, running integration tests, and so on. All of these kind of like automated system tasks. So we didn't want to write them in C++ because that's kind of heavy-handed for doing those kinds of tasks. Doing it Lua is kind of painful too, because for these tasks you typically need lots of utility classes. You want to access Git, maybe you want to access SVN, you want to start running operations and running executables on your machine, and do all other kinds of tasks that you might need libraries for. And Lua is kind of the philosophy of Lua is more like no libraries, everything is a custom library, which means you have to download it, make sure it's available for your platforms, you have to upgrade the versions and so on. Whereas Ruby comes more like batteries with batteries included. It's like so you can use Ruby more like a shell language almost. It's available. If you have it, you have most of the stuff you need available. Of course, that's not true, because eventually you'll have to resort to gems anyway, which brings you back into the same kind of messy situation. But at least when we started out, we thought, well, we can do most of this stuff just using standard Ruby, and it's kind of nice to use a batteries included language for simple scripting like this. So that was the reason why we used Ruby originally. I would say that like now, when we've added more languages into the mix, we've added C# and we've added JavaScript. Having Ruby there is not super nice. So I would think that if we would done this in the future, like if we would write these scripts as the situation is right now, maybe we would do them in JavaScript instead and use Node.js, so that we don't have another language in the mix. Right now you can't use other languages to drive the tests, but I mean the testing framework is really not that big. It's all it does, it starts up the engine, and it starts a WebSocket to communicate with the engine and send a few commands. So rewriting the test framework, the integration test framework in another language wouldn't be a huge deal. You could quite easily do that. Input. The engine seems to provide a fairly raw kind of access to user input, with enumerating what button access are available, getting input events or measuring deltas from them, etc. Other engines such as Real prefer to provide a higher level of abstraction, where various inputs from different controller types are mapped onto more conceptual actions. For example, mapping A on the Xbox 360 controller and enter onto an accept action. Does Stingray offer anything like this? Should it? Is there any design philosophy for avoiding this kind of thing? This is the most common typo among programmers, by the way, since strings are so common. Everyone writes Stingray all the time. Yeah, I mean, the design philosophy here was that it shouldn't really be needed because a user could easily create this mapping in Lua anyway. So why should we add some static system for it in the engine, which might not do all the things that the user might want to do? For example, what if the user wants like gesture recognition or like keyboard combos, or there's so many the designs while doing like a simple mapper is easy to do. The design space for doing complete UI mapping is kind of big, and there might be states and modes where different actions should do different things in different modes and so on. So that's basically like the design philosophy. This isn't a performance critical thing, so there's no big reason for having it in the engine. It might as well just be in Lua, and then you have all the flexibility of doing whatever kind of crazy system you want with combinations and codes and multiple key presses at the same time, or whatever your system might need. So that's the main reason for it. We don't want to, when it comes to these, we want all the stuff that requires high performance in C++ side, but when it comes to stuff like that doesn't really require high performance and where you can imagine lots of different designs, we'd rather just have it in Lua and give the users the full flexibility of it. So I realized that this might be an issue for like beginning users who just want to start with something. Then they sort of have to write this system in Lua themselves, and they don't have like an immediate offering of this. So maybe this is something that we should offer in sort of our app kit layer for Lua. Like here's our standard way of mapping controllers, and then you could get up and running more quickly with this kind of thing. But I still think it's the right decision to have this in Lua rather than in the engine for the final game. Entities. In the inheritance system for entities, you're allowed to add and remove components from the parent as well as overriding them. You mentioned that this can lead to some confusion about where things are added and removed in the inheritance hierarchy. This definitely matches my experience of working in a similar system. Does Stingray offer any tooling to help track down where components and their values are coming from? Yeah, so this is more of a tooling question, which means I'm not really the right person to answer this, but we do have like basic color highlighting to distinguish between a value that is overriding the component and a value that is and a value that comes from a parent. I don't know if we have a system for like finding the parent in the component chain. I don't know if there's a tools person on this talk here right now who knows if we have a system for that.
Sorry, can you repeat the question?
The question is like when you have an inherited value, how do you know where that inherited value comes from? So there might be a long chain of things that you inherit, and somewhere in that chain the value is changed. Do we have some way to track down where a component comes from, what parent in the inheritance chain it comes from, or where?
Well, the tooling builds a dependency graph basically of all the entities that you're currently working on. So is this yeah.
I guess what they're asking for is something in the UI. If you could like right click on a component and say like, oh, find the entity in the inheritance chain where this component was added.
Yeah, it's not currently supported, but it can be.
All right, yeah. Cool. One problem I often come across through the entities is component coupling. Components often need to communicate between each other for one reason or another. What is Stingray's approach to this? Well, the approach here is it's kind of explicit communication, accessing component instances in other components and getting and setting their values or performing operations on them. And I talked earlier about how to do this efficiently. I'm not sure if there's anything more to say on this. Our take on this is to do this with explicit communication. Another issue I had with component system is that they often lead to either an additional level of indirection for every operation or writing a lot of wrapper functions. For example, for moving a unit, you might want to say my unit move xy. Under an entity system, I often find I either had to write my unit movement component move xy in each place, or alternatively, for every method, I had to write a function like void unit move float x float y movement component move. Does Stingray have this problem, and do you consider it an issue? If so, do you have a preferred approach to solving it? Yeah, I mean, we definitely have this issue, but since one thing to notice here is that you don't really do it this way in Stingray, since it's not like an entity has a list of components that it have. You always talk to the component. So in Stingray, you could do this with, you would talk to the transform component, which is the transform component manager that owns all the transform components for all the things. And then you would do set position, and you would pass in the entity and the new position. So this is how you set position on an entity. Now, if we compared it to how it works in the old unit system, it would look like this: unit, set position, you pass in the unit, and you pass in the position. So in our engine, it's not really a big difference between these two approaches. They're pretty much the same. So there's no additional like typing or anything to do this in the entity system. I guess the thing here is that the thing is probably our layout, the way we've laid out this system, so that we're dealing with transform component managers rather than component instances, so that you can well, I guess this yeah, with component managers instead of component instances, so that you don't have this sort of extra indirection step. Or I guess maybe you have, because you need to grab the instance of it. So you would have, yeah, I guess you would have the same issue actually, because you would get the component, you would have a lookup here of the instance, right? Yeah, so I guess it does become a bit more writing with the lookup here, and you would have to write your own wrapper functions in order to get rid of that. I don't know if this is a problem. Maybe it is, but I'm not too concerned about like these wrapper functions in this case. I mean, it's not much Lua code to create your own wrapper like this. Maybe it's form component wrapper set position equals function cross, and then just having this call here. I mean, I don't know if it's that much of a big deal to create this wrapper, and then you can have form component yeah, yes, call it the same way as you would call it for the unit. So I don't think it's a big deal to create these wrappers. I mean, you could say like, well, what about the inefficiency of having to create a wrapper? Well, if we sort of baked this lookup in, as I said earlier, then you always have the inefficiency. With this approach, then you have the option of having the inefficiency or not, which I think is an advantage. So yeah, it becomes a bit more overhead with the, or not overhead necessarily, it becomes a bit more typing with the component system. That's sort of the price you pay for the abstraction of having everything having an additional abstraction layer where you could add new functionality into a thing. So yeah, I'm not sure it is a problem. Maybe it is. Maybe. Multiplayer. It seems like the engine is using UDP for performance reasons, but then has a built reliable packet system on top of that. What is it that makes Stingray's custom reliable packet system faster than TCP? My understanding was that the reason TCP was slower than UDP is because it does something pretty similar to Stingray's own system with having to buffer packets, resend, etc. Well, we have a reliable packet system on top of UDP, but we don't only use the reliable system. We also use an unreliable system. We also allow sending of unreliable data, so we can combine both in the same system, which means that we only pay the overhead for the reliable data. And in addition to that, we also can control like resends and stuff like that, and optimize it according to a particular application's needs. Like, does this application do we need to resend? How do we have room to send more data right now, and so on? And we can do our own adaptations of that, and that's why we use that. And it's, as far as I know, it's the approach that most multiplayer games do. But I don't know. I think it's in some cases it might, for certain applications, maybe doing just TCP could work as well. But we like having the additional amount of control for this situation. But there are advantages to using TCP too, like because routers and stuff has information. Routers and stuff can reason about TCP, so they can reason about resends and stuff in TCP and perhaps treat it a bit more efficiently. Whereas routers don't know anything about our special protocol that we built on top of UDP, so they aren't supposed, they can't really do anything special about our UDP packages. So I know there's been like discussion of this, like, oh, with these router things and stuff like that, maybe it does make sense to use TCP for these things, but I'm not sure. I'm not sure what the status is right now. Maybe you can use TCP and you can get it to work with performance close to UDP. I'm not sure actually. Maybe what the current state is. Maybe it is possible. But UDP is the thing that has been working for most of the time, and as James said, it's what Xbox Live and other services do too. So it makes sense for us. Does Stingray's communication or transport layer perform any decompression beyond packing multiple messages into a single packet? If so, what kind of compression heuristics do you use? Well, we use range reduction and bit packing, as I talked to in the message, but we don't use a generical compression algorithm on top of that. You could like plug in zlib or something like that on top of that, but we don't do that. And for usually if you do your range packing in a good way, there's limited benefits from plugging in additional compression on top of that. In addition to that, you have the problem that you're kind of performance critical, so doing a lot of compression and decompression might be a problem. Also, the packets are kind of short, so you might need to think about state when you compress and decompress, like how much you can't really save any headers for each packet, like compression and decompression headers, and they might arrive in a different order. So doing it sort of a stream compression decompression doesn't really work, except for the reliable messages you could do that, but for the unreliable messages that becomes tricky. So it's kind of tricky. I've seen some systems, when I've looked at network systems, I've seen some systems that use compression and decompression for string data. So if you send string data for, they use it. I think it would make sense to use it for sort of an initial synchronization package. Like when you join a game, you want information about all the objects in the world, and that's like a big chunk of data. It might make sense to compress that initial chunk package and send it to a client that is just joining. Unfortunately, in our network system, we don't really have a concept of a synchronization phase like that. We don't have, oh, now he's joining, so now he gets this big chunk of data. Instead, our synchronization, it works the same in the initial phase, like when you join. The other clients will see that you don't have specific objects and you don't have updates for specific objects, so they will send you that update, those updates. So it works the same when you're joining as when later in the game when somebody creates a new object and you don't have data for that object. And that is kind of nice from like a system design perspective, because it means we don't have a special case for handling this situation where someone has just joined. It works just the same way as it does later, so we don't have to reason about yet another state. As I said, the network system is already kind of complicated to reason about, and yet adding yet another phase, another state to think about would complicate it even more. But the drawback is that we lose the opportunity to do that initial synchronization really efficient by sending like a zipped packet at that point. And the reason we don't use setlib for string data is typically we don't send a lot of strings. I mean, usually just text chat messages and stuff. It's not usually a need to send a lot of string data, so that hasn't really come up. You mentioned that the engine offers a pre-built system for using game objects to synchronize units. Will something similar be available possible for the new entity-based system? If so, how will it work? Will components be responsible for syncing their properties with game objects? Haven't really thought about this. It is something we could add. I'm not super into, to be honest, I'm not super into the automatic synchronization system for units. I don't think any of our clients is kind of using it because they want more detailed control over the synchronization. I'm not sure about this. They might be using it, but so I don't know. But I think it would be useful maybe to have, I think it could be useful to have these two levels of system because some of our users, there are some people who just want to do network and they're not super interested into performance because maybe they're not building a multiplayer game. Maybe they just want to do some shared experience, like, oh, I just want two people to be able to walk around in the same virtual museum. And they might not be super interested in thinking about how to really super optimize the network. And they might not want to deal with all the complexity of doing that. So I think it might make sense to have like a higher level of synchronization for people who don't want to get into the details, where they can just maybe have like an entity synchronization system and say, oh, I want to synchronize these and these components for these and these entities, and then everything happens automatically. That could be a really nice system for people with those kind of use cases. So I think it could be an interesting thing to do, but it's not something we have really thought about at this point. And maybe if we do it now when we have the plugin system, we would do it as a plugin rather than as a core part of the engine. Does Stingray offer an approach to localization? If so, is there anything you can say about that? Yes, we do have localization. Localization in Stingray comes in two flavors. We have localization. Kind of think I talked about this in the resource talk. What we have is we have two separate systems. We have one localization system for strings, and that is just a lookup table from string ID, like file ID, and then what that should be translated to in different languages. just a JSON file with these translations, and then we have lookup functions. We load that into memory, and we have lookup functions for looking that up. So that's a string localization system. Then we have a resource localization system based on suffix mapping. So if you have a resource like this, you can add mappings, suffix mappings in our setup that should be used, that are connected to either platforms or flags. So for example, you could say that on PS4, the platform is PS4, we should use .ps4 suffix mapping. And that means that if there is a unit called tree.ps4 unit and we're running on PS4, we should use that unit. So in that case, that unit will take the place of the original tree unit. We can use the same thing with flags. So we can set up a suffix called French, and we can say that the flag is French. And that means that if there is a unit called tree French unit, and we're running with the French flag set, then that French tree will be used instead of the original tree. And these flags can be mapped statically during compile time of the project, and that's what happens with the platform flags. So when we compile for a specific platform, only those platform-specific resources will be included. But they can also be set up dynamically, allowing you to dynamically on the fly set the French flag. So that's typically what would happen in a game. You would have an in-game menu where you selected the language, and then you would set the French flag or the Japanese flag or whatever flag language you wanted to use. And then once that flag is set, all the lookups, when the engine tries to look up the tree resource, would then be diverted to this French tree, and you would get the right property. So that way you can localize pretty much anything in the engine. You mentioned in the container talk that Stingray makes use of optional and error types from error handling. Could you say more about the general philosophy behind error handling in Stingray? Are exceptions ever used? How about return codes? So it's kind of a big question, but just to go through it shortly, we don't use exceptions at all. I don't like exceptions as an error handling mechanism, and I don't like it because it introduces a weird control flow that is kind of invisible to the user. So when you write code like this, you write blah blah blah, and if blah blah blah, blah blah blah, and blah blah blah. And if you try to understand, if you come into this code that someone else has written and you try to understand it, you go to the code and say, oh, it does this. Okay, then if this, it does this, and then it does this, and then it does this. But if you have exceptions in the mix, they kind of mess with all this, because then it might be, oh, this thing called something that called an exception, so actually it won't do this. It will jump out of this thing up to some other thing up here, far away, and do something completely different. And I think that just adds so much complexity in trying to understand the code, and weird code flows that are impossible to understand. I think pretty much, yeah, I don't like that system at all. I like systems where error handling is explicit and you can see what happens, and you can see where the error goes and what happens when the error occurs and so on. So that's why I don't use exceptions. We don't use return codes in Stingray at all. I'm not too fond of return codes either, because they tend to be like these random numbers that just end up somewhere and then they get propagated out, and you typically don't know what to do with this random number. You can translate it to a string, but then if you do that, you get like invalid access error or something super unhelpful like that. So I don't like this kind of error handling either. So what we use in the Stingray, is we actually use strings mostly as our error messages. So a function returning an error will return string instead. So, and the string will be some descriptive message. So could not open file blorg, and then that string, which is allocated by a special function, which I've already talked about, so I won't go into that anymore. But that string gets propagated out and eventually displayed to the user. And there are disadvantages to this. For example, if you want to automatically process the error some way, you can't really do that because it's just string data that you can't reason about. But I find that there's very rarely that you want to do that anyway, and that kind of error. So I think this is kind of a good approach, because you can always get a reasonable description of what the error that occurred was, and that gives you some idea of dealing with the error. Yeah, there are much more to say about like error handling in general, but let's continue. Similarly, I remember you saying about moving away from the crash and error approach because the impact this has on the rest of the team in case of mistake. Could you say more about defensive programming in Stingray? How defensively is the code written? For example, if you use an error type and getting a pointer and there's no error, would you null check the pointer too? I would say that, so it's kind of a tricky question. I would say that it's not very defensive. So I think that with error handling in general, you need to think about why and what to do about it. Like, what kind of errors do we want to deal with, and what can we reasonably do about them? So there's a kind of defensive programming where a program tries to cope with errors in the program itself. So typically you have some function. Say we have a function open file. Open file, you get passed in a file name. Now, if you're in this mode, if you're like defending against, if you're writing a program where you're defensive against your own programmers, you would do things like, oh, what if this is a null pointer? If name equals null, do something. Oh, but what if it's not a null pointer, but what if it's an empty string? That's an error too. So if name is an empty string, oh, do something. Oh, but wait, what if name points into what if name points into freed memory? So can I check this with my memory system? Memory online, does this pointer actually points to memory that is mapped to my application? No, do something more. Oh, what if it contains characters that are not allowed in string names? Oh, what if a bad character, blah 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 blah. And so this is kind of a, in my opinion, if you start doing this, you end up like going into this deep hole of adding more and more and more things to possibly think about that some of your own programmers could do to this function, which is a lot of work, a lot of busy work, just adding all these tests. And there is not much point to doing this unless you have a way of doing something that is better than crashing. Because if you're fine with crashing, then you can just ignore all of this because it will probably crash anyway. So there's no point in adding all this unless you can do something better than crashing. But what can you do in this case? So the user wants to open something, but you can't do it. well, you could return some error code to the user and so on. But if the user is passing in null to open a file, what will the user will the user do something reasonable with the error code? Probably not. So I think this kind of defensive programming, like defending against errors that your own programmers make, is kind of pointless. I think in these cases, if your own programmers make an error, just make sure that it crashes. If you have some situation where a bad value could come in that wouldn't cause a crash, you could just add on a search so that it will crash for sure if that value comes in. So, or rather, so that you get the crash early rather than an error later. But I think that the best way of dealing with errors made by your own programmers is to just make them crash, and that will point people to the error and make them fix the error, rather than saying, oh, we should somehow be able to deal with our own programmers passing in a null pointer, and the system should somehow magically be able to recover from that and figure out something useful to do, which I think is pretty much impossible. You could, I guess, jump out to the main loop and just continue running as if nothing happened, which again might not be the best solution. So I don't think it's a good idea to be program defensively in that way. So what we mean by defensive programming is that we're defensive against user errors. So the idea is if the user makes an error, if a user types something in a dialog box or writes something in Lua, because Lua is a user interface in our view, that shouldn't crash the application. That should lead to like an error message that the user then can handle and proceed. So we're defensive against the user. We're not defensive against our internal programming errors. For those, we just crash as early as possible and make the person responsible fix the problem. Okay, 2 final questions. You mentioned several talks to design decisions around backwards compatibility, particularly in regards to the plugin system. Do you have a philosophy about managing backwards compatibility overall? Do you believe you can ever drop support for a feature? If so, when? There were many systems using this to do with refactoring or that had already been refactored. How do you avoid building up numerous legacy systems? For example, will you ever drop the old unit system? Or do you think once entities are fully matured? Yeah, I mean, this is I think this is not really a programming question. It's more like a business question, maybe. I think from a programmer perspective, we like dropping backwards compatibility. It's the best thing to do. Like, backwards compatibility is a pain in the ass. It creates a lot of problems. It makes your test space much larger, and so on and so on. So from our programming side, we certainly try to avoid backwards compatibility in the way that we make our system so that there are backwards compatibility as far as possible. But when we need to make big changes, we want to be able to drop backwards compatibility. So when we do big rewrites, we tend to offer migration solutions for the users so that they can migrate most of their data to the new system so that we can drop the old system. And so we tend to do that. We tend to drop support for old stuff when we don't have a big user base that use it. But again, that's more of a business decision. It's like, yeah, how important are old users using this system? What can we do to help them, and so on. I mean, I think saying that you're never going to drop any feature, dropping feature always makes users unhappy because there's always someone using that particular feature. But saying that you're never going to drop a feature puts you in a really awkward position where you're just bloating your code more and more and bloating your application more and more. So yeah, I think like encouraging users to transition to new systems, providing migration tools, saying, well, the old system will probably go away someday. And what we also can do is like, well, you can use the old system, but you're responsible for maintaining it. Here's the source code. good luck with that. It's another thing we can do in order to drop old systems. But as for the question of when in time to drop an old system, that's like, yeah, when most users seem to have progressed to the new system, then we do it. We of course always do it with an overlap. And for big systems, like typically in the game industry, you have like a year maybe for a project, or 2 year maybe, where a project is in active development against like a changing, where a project would take updates from us to the engine. That's maybe a year or maybe 2 years, or maybe a bit more than a year. Because after that, the project typically want to lock down their source code anyway and move on. So that's sort of the time scope in which we can drop a system. We would, whenever we make a new system that completely replaces an old system, we would keep the systems in parallel for a number of years, so that to give users ample time to transition over to a new system. And I think that's what we will do with the unit system. We will eventually drop it, but we will keep it parallel to the entity system for a number of years. And I think we will do it in some kind of compatibility mode. We have a kind of entity component that is a unit component, which is essentially just a way of wrapping a unit into the entity system. And I think we will keep compatibility through that layer for a number of years, and then we will eventually drop the unit system. I don't believe in keeping things on forever. We have to move forward, or the code will just get too bloated and die eventually. So things need to be dropped. Okay, final question. Finally, I know this is a bit vague, but could you say any more about your general philosophy on developing a general purpose game engine? You mentioned several times the idea of paying for what you use. Are there any other principles you try to follow when designing the engine? It feels to me like designing a single framework to support things as varied as mobile tower defense games through to first-person multiplayer console RPGs, and everything in between must be incredibly difficult, especially when you don't want to burden the mobile tower defense game with all the weight associated with a giant AAA console game. Yeah, there are, I mean, we had a number of principles. When we started designing the engine. So we had a principle of simplicity, keep things as simple as possible, and that's because we think that simplicity brings enormous value in the long run, because when you keep things simple, it makes everything else cheaper. So, for example, suppose you can add a really complex system to your engine, but it optimizes things slightly, so your engine runs a slight bit faster. That might not be worth it, because over time, the cost of maintaining that really complex system and the cost of everyone involved with the engine understanding that complex system and dealing with it, that will eat up a lot of time that could be used for other optimizations. So it might be that having the simple system, and instead of taking all the time that would have been invested over the entire lifetime of our product into the complex system, taking that time and investing it into other optimization might actually result in a faster overall engine. So even though this system, this complicated system, is an optimization, it might, in a bigger perspective, where you consider gain versus effort, it might actually be a de-optimization. So that's why, just one of the things why I think simplicity is so important for having a good code base, and having a good code base is what makes you make improvements, and that's what allows you to have a better code base in the future. So that's one of our design guidelines. Multi-threading and high performance, which was one of our initial design guidelines, and paying for what you use is part of that. What else did we have? We had flexibility, being data-driven and flexible as one of our guidelines. And that sort of addresses this issue. we didn't want to lock the user down into choices. But instead have a flexible rendering pipeline, having systems where you don't pay for more than what you use, and that by having that flexibility allows us to cover all different kinds of games and all different kinds of platforms. Now, I would say that is a truth with some modification, because even though we've just designed everything to be fully flexible to cover this entire range of devices, there will still always be a focus. Like, what are we focusing on right now? What are the problems we are focusing on solving? And those areas will get a bit more attention, and we will have more performance and better running in those areas where we have attention. And the intention is controlled by what our customers want, both the customers that are using the game engine and what like Autodesk as a whole wants, like things like VR, hot right now, of course. So that means our attention is focused on VR, which means like we are putting in optimization specifically for VR to make that more efficient. But the general idea is to have a flexibility across the entire range of devices, and I think we do really well there. We have released everything from simple mobile games to high-end AAA titles. But of course, there is always a focus somewhere and less focus at other places as a consequence. The final design principle we have was what you see is what you get, like quick iterations. We want you to be working in the real stuff, like not like you do a change and then you wait 2 days for a build and then you can look at it on your final hardware. You should always see what you're working on as much as possible and see the real stuff, the real visuals, the real performance, the real everything. So that's our principles, and yeah, it's a difficult. Yeah, it is kind of difficult to make it all work. But that's our job. If it was simple, everybody would do it. That's all the questions I had were submitted. Are there any other questions from the people online? I know we're already a bit over time. All right, if not, thank you very much, and this concludes this series.
Thanks a lot for these presentations, Nicholas.